Do I need to bring the air horn every day? I don't need to, but you want me to? All right, let me begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you just guide our steps today and just help us to understand a little bit about work. In your name we pray, Lord Jesus. Amen. So let me get into it. So we are going to begin our discussion of work and energy. So the first order of business is we need a definition for work. What is the work done by a force over a path? Well, here it is. Definition. The work done by a vector field F over a path C, which is parametrized by R, which is going to be a function from, let's say, T1 to T2 to, well, let's keep it three-dimensional for the moment. All right. Is given by the integral below. So we'll call the work W, and it's going to be equal to the integral of F dot dr over the curve C. Now, if you've already had calculus 3, wonderful. You know what this means. Or you'll learn what it means if you're in calculus 3 in about a month. But we cannot wait for this, so I must give you the definition now, right? So here's the definition. The definition is simply this. We integrate from T1 to T2, all right, and we take F, we take the vector field, we evaluate it at the path, which is R of t, all right? And then you take the dot product of the vector, take the dot product of the vector field with the velocity, which is dr dt, and you integrate that thing over time. So that's actually how we would calculate the work for a given force field over a given path. All right? So this is the definition of work. We can look at some special cases, all right, to make life easier. Like one special case I'll work out real quick here. Example 1. We could have a path that, say, goes from, you know, position R0 over here to position R1, right? If you have a path from position 0 to position 1, how would you parameterize that path? Do you guys know? Well, one way you could do it would be this. You could say R of t is equal to R sub 0 plus parentheses 1 minus t R sub 1. Wait a minute, is that right? 1 second here. Okay, so sorry, I've lost my way here. T times R1 minus R0. I think that works. Is this a parameterization of that path? Is there a question? The talking in here needs to stop, please. Thank you. So R of 0 is what for this one? And what's R of 1? Is there a question? I keep hearing whispering in here. So R of 0 is what? When you plug t equal to 0 into here, this drops out, right? And you're just left with R sub 0. When you plug t equals to 1, what happens is you get R sub 0 plus R1 minus R naught, which gives you back just R1, all right? So what we're looking at here is a formula that parameterizes this path. In other words, at t equals to 0, you're here. At t equals to 1, you're over there. Okay? So this is the parameterization of a path. Now that we have that, we could calculate the work done by a force along this path, all right? So let's let our force be really boring. Let's let F just be a constant force, F naught. So this is just a constant force field. All right? Constant force field. Like the gravity force to our approximation is a constant force field in here, right? Okay, so, all right, let's calculate the work done then. So the work done, right? Let's do it. The work, integral, let me call this curve C, right? So how's it actually going to work out? Integral from 0 to 1 of F naught, right? Dotted with dr dt, right? Integrated over time. This would be the work done by this constant force over this line segment. How does that calculation go? What is dr dt here for this path? Can you guys tell me? This right here, how does this differentiate? What do you got? What's dr dt for this? So the r naught's a constant, right? That differentiates to 0. Derivative of t is just 1, right? So this just leaves you with the displacement vector, r1 minus r0, actually. All right, so that's what dr dt is in this case. So we're just looking at the integral from 0 to 1 of f sub 0 dotted with r1 minus r0. That's my velocity in this case, all right? And what does that work out to? Well, this is a constant, right? Like this is just a number. For a constant vector and given pair of points, this is just a constant. So we can pull that constant outside the integration, and what are we left with? Basically, since that's a constant, I can take this integration, right? Watch this, guys. I can take this integration and I can rewrite it over here like that. See, because this is a constant, I can pull it out of the integral. What is the integral of dt from 0 to 1? Just 1, right? So what you got? You've got f sub 0 dot product with r1 minus r0, right? Or perhaps the thing you remember from high school physics. You know, I have been laboring under the incorrect assumption that many of you have not had high school physics. Show of hands, who has had high school physics? Yay, all right. That was not the situation always. Like in the past, maybe I'm thinking of 201, but like, man, there has not been everyone having high school physics before, so I'm happy that you've had that, because you should recognize this formula once I write the next line. Can you recognize it? Work equals F0 dotted with delta R. See that? Isn't that the formula that you know and love for work of a constant force over a displacement delta R? Yeah? Remember this? No? So this highfalutin calculus 3 definition reduces to work is force dot displacement in the case what? In the case that the force is constant. Right? What if the force is not constant? What's the work done in that case? Well, here's an example too. So this one's, you know, suppose you've got a plane, right? You got a plane and you're pushing a box. That's supposed to be a box. I tried. Here's Mr. Top Hat. He's pushing a box, right? And he takes that box and he pushes it along a circuitous path, right? All right, like that, all right? So he pushes the box along this crazy twisting, turning path along the plane, right? And suppose that this box has a mass m, right? Box has mass m, right? We can take a snapshot of the box at any point along that curve. I'll just draw it over here. Like here's the curve, right? The box is on there. You're pushing it along. What's the story? If you're pushing the box, Mr. Top Hat's pushing the box, he's going this way, right? That's the direction of the Let's suppose that Mr. Top Hat is pushing on the box, you know, essentially horizontally, okay? So there's the pushing force. Where's the force of friction in this case? So that's also what? Parallel to the velocity of the box, right? Which would be dr dt. Agree? Disagree? Sorry. Where's the force of friction in this case? Force of friction goes where? Opposite direction of motion, right? Here's your force of friction. What's it equal to? If nothing else is going on, we've got what? The normal force like so, and mg goes down, right? So my force of friction, right? What's the force of friction? Force of friction, as a vector, we can write a formula for it. In this case, in this context, what is the force of friction? Notice that the velocity we could also write as the speed times v hat, right? It's the speed times the unit tangent, all right? Speed times the unit tangent. And so a formula for the friction force is this. It's minus mu s times the normal force, which in this case is mg, v hat. That is a formula for the friction in terms of its direction. It's opposite the direction of motion, right? So my question then is, what's the work done by friction on this mass as you push it along this twisty-turny path? Can we calculate that? I think we can. Let's try it out. So I'm going to call this curve, this crazy curve, I'm going to call it C, all right? And so here we go. The work done by friction let's calculate it. What is it? Integral over this path I've called C of the force of friction dotted dotted with dr. Now, okay, that's a lovely sentiment, but what does that mean? That means we have to find a parameterization for the path, right? Which I'm not going to do because it's a crazy twisty-turny path that I just made up. So we have to work symbolically here, right? Conceptually. But anyway, there's some time, say t1, it starts at t1, and it ends at t2, okay? So we can integrate from t1 to t2, whatever that is. And what is the force of friction? Well, it's minus mu s. Mu s? What's wrong with me? Good gracious. This is definitely moving, right? So k, mu k, big mg, and then v hat, and then I dot with what? I dot with dr dt, right? But to save myself some writing, rather than just writing dr dt there, I'm going to write v hat. Speed times v hat dt. So this, what I just wrote in parentheses there, is just me writing dr dt in a sneaky way. And the reason I'm doing that is simply that I can then do the calculation, right? Maybe you can recognize what's going on. So what happens with v hat dot v hat? That just gives us what? What's any unit vector dot itself? It's 1, right? Because it's the length of the vector squared, which is 1. So that gives me 1. And this just becomes minus mu k mg, all right? Minus mu k mg times what? Times the integral from t1 to t2 of v dt. Now, what is v? V is ds dt. I went into more detail than I should have about that, about day 2 in here. So v is, in fact, the derivative of the arc length function with respect to time. So really what you're integrating here is ds dt times dt, which means, what is this integral? If you're integrating the change in s with respect to t over the time interval, what is that? By the net change theorem in Calculus 1, which you've had. S, right? The change in s, which is also known as the arc length of the curve. So what I just boxed, that's the arc length of the curve. So the answer, the work done by friction, is simply the force of friction, right? which is mu kmg times what? Times the length of the curve. So this fancy schmancy calculus 3 definition of work also works for curved paths like this. Does this make sense? Like, think about it. The work is negative. Why? The work done by friction is negative because it's always opposite the direction of motion, right? Are we good? Let's do a even easier example. Example 3. You've got a force which is perpendicular to dr dt equals to v along C. What's the work done? What's the work done by such a force if we're integrating f dot dr along a force which is perpendicular? What does that mean? The dot product of a force, if the force is perpendicular, sorry, not really, but sorry, well, I debate. Anyway, so this, when we calculate it, is what? F dr dt. What is F dr dt? By assumption, it's 0. So you're integrating 0, which gives you the work done is 0. In other words, we have, perhaps, if you believe me, derived the result that if your motion, right, is perpendicular to the force, always, that perpendicular force does no work. For example, as I move this chair, this is a nice chair for this, isn't it? As you move that chair, I am doing work against the force of friction's doing negative work in that motion, right? I have to oppose the friction to keep going. What's the work being done by gravity on the chair during that motion? Nothing, right? Because it's not moving vertically. So, I mean, more to the point, the motion is horizontal, gravity goes which way? Perpendicular direction, right? So work done by gravity, 0. Okay, so must be a test over there. Let's see here. I don't think Sprano teaches over there. It sounded very Sprano-like, but anyway, so constant force gives us this, right? What's another case you can think of? How about the case that we're one-dimensional, right? In one-dimensional motion, what does this look like if your motion's just along one dimension? How does this formula simplify if we're in one dimension? So, example 4, one-dimensional case. This just becomes the work is equal to the integral from, say, t1 to t2 of f of x of t times dx dt dt. So that's what this integral looks like for one-dimensional motion. If your r of t is just x, if it's just one-dimensional, it's that. And you guys have had calculus 1, yes? So you know the U substitution theorem, yes? What does this integral become then in calculus 1? You can change the variable from t to x, and this just becomes the integral from x1 to x2 f of x dx. So to calculate the work done by a one-dimensional force, we can just do the integral over x. So that's a special case, a very special case of the work integral. But the genuine work integral is three-dimensional. It allows for non-constant forces. It allows for paths which are not lines, paths which could be circles, ellipses, whatever. It's completely, it covers all cases. Look here, how about Hooke's law? What's the work done by the Hooke's law force? If we have F equals to minus kx, how does that work out? The work done from x1 to x2, what is it? How does that work out? You get yourself a minus 1/2 k x squared. Evaluate that thing from x1 to x2. What you got? You got minus 1/2 k x 2 squared minus x1 squared. So there you go. There's the work done by a spring as it goes from x1 to x2. This is the work done by a spring. Okay? When do we need an integral? When don't we need an integral? When do we need a dot product? When don't we need a dot product? These are questions you should think about. I'll give you the answer. We don't need an integral when the force is constant. Right? In that case, we can take the force dot the displacement. That gives us the work done. We do need a dot product, though, because it does depend on the direction, right? If the force had been perpendicular to the displacement here, the work done would have been 0. And that's covered by this dot product. All right? The dot product, what does it mean? This means the part, this measures in some sense the part of the force which aligns with the direction of motion. That's what the dot product does. It measures the part of the force which is in the same direction. The larger the dot product is, the closer the vectors are to be in parallel. Okay? If the dot product is negative, that means they're anti-parallel, opposite directions. When do we need an integral? When the force is variable. When the force is variable, we need an integral, for sure, right? And so in this one-dimensional case, we don't need dot product because it's just one-dimensional, but the integral takes care of the fact that, like, the spring force is variable, right? So I can't just take the spring force times the distance. That wouldn't make sense because the spring force is varying over the displacement from x1 to x2, right? So I need to integrate to calculate the work done. All right? Does this make sense? I hope. Okay, so these are some basic examples. So far, I've only showed you how to parameterize a line, right? Pretty much in here, there's two things I want you to know how to parameterize. The one is a line, and the other is a circle. If you can parameterize a line and a circle, then you're good to go for my physics class, all right? That's what you got to learn. So example 1, how to parameterize a line. It's right here. Yeah, that's it. Circle we'll get back to. But before I do that, I need to prove a theorem for you. Because, you know, if this is all that there was to work, it wouldn't be that interesting, right? But there's something really, really neat that happens with this concept of work, and it's why we even talk about it. So let's get to that. This is known as the work energy theorem. So, I mean, I will confess to you guys, I'm following my notes. You can look at the book, and that's fine. But I think to understand what's going on in here best, the wise thing to do would be to try to follow along. And for example, like lecture 15 is where I am right now. Not that I'm going linearly through it. What I'm doing is based on lecture 15. It's not literally what I have written here. There's a little bit more in here than I'll ever be able to write on the board. But that's where we are, lecture 15. Work energy theorem, what does it say? The work energy theorem says the following. If F is the net force on mass M, then the work done by F over C, a curve C, is the change in the kinetic energy. Now, admittedly, we haven't defined what kinetic energy is yet, right? So let me do a calculation which will show you why we define kinetic energy as we do. All right, here we go. So we got the work. And that's equal to the integral from, let's say, T1 to T2, right, of the net force F evaluated as the parameterization R of T dot dr dt. So far all I've done is write down the definition of work. All right? Now, this is the net force, right? What does that mean? What special rights and privileges does that earn this force? What's its relation with the position vector here? So this was a problem on the test. Some of you have not fully embraced the idea F is equal to ma. There were several problems, F equals to ma. And that's like all you were missing, like multiply by m. You had it right, you know? But so this is m times a. So let me write that down. This is equal to the integral from t1 to t2 of m times a, right? Now I'm going to write a as dv dt because that will serve our purpose. And I'm going to write that as v because that will also serve our purpose. All right, so that's really m dv dt dot v. Check this out. Something very sneaky. Check this out. So if we do v dot v, right? And you differentiate that, what happens? What's the derivative of a dot product? Guess what? There is a product rule for dot products, just like there's a product rule for products. So the way this works is dv dt dot v plus v dot dv dt. In other words, what are you looking at? You're looking at, but the dot product's commutative as well, right? So what we're looking at here is 2 times the velocity dot the acceleration. So what is this over here? What is that really? It's nothing more than the integral from t1 to t2 of m over 2 total derivative of v dot v dt. Now what's another way of writing v dot v? That would be the magnitude of the velocity squared. We could also say it's the speed squared, right? So you could simply write v dot v is v squared. That's our notation for speed squared, yeah? So I can bring the m over 2 inside. And then you guys will remember from your high school physics probably that 1/2 mv squared is the kinetic energy, right? 1/2 mv squared is the classical kinetic energy. And what do we have? We have the integral of a total derivative. So how's that go? It goes away. So this is this is nothing more than, kinetic energy at time 2 minus the kinetic energy at time 1, which I usually just denote that by like KE2 minus KE1. I forget the symbols I use. Sometimes I'll use it. Sometimes people use a T for kinetic energy. Sometimes people just use a K for kinetic energy, but I'll just be really clumsy and use KE for the moment, if you don't mind. You stay down there. Let's see here. KE2 minus KE1, where of course I mean the kinetic energy at time 2 minus the kinetic energy at time 1, right? And how am I defining kinetic energy? Kinetic energy is 1/2 mv squared. So this is the work energy theorem. When does it apply? Anybody know? What are the terms and conditions for this theorem? It's written right there, right? So notice that we do need, it's the net force, all right? So when you're dealing with the net force acting on a mass, the work done by the net force is equal to the change in kinetic energy. Now, this in and of itself is interesting, but where it really comes to life is when we introduce potential energy, right? So what's potential energy? How do we get to that? What's the story of potential energy? Well, in order to talk about potential energy, I have to introduce the other half of Calculus 3 to you today, if that's okay. Yes, no? No? Okay. It's too soon after the test? Sorry. Don't drop. Did I mention that I replaced the first test grade with the grade of the final exam, if helpful? So all is not lost. If you did badly, you can do better on the final, and then, then the whatever happened will be replaced, will be forgotten, and I will replace the final exam grade if it's helpful. Now, there are some of you who made a high grade on this test, and you won't probably do that, right? You're like, someone made a high grade on this test? Yes, someone made 145 on this test. Yes, it happened. And then I added 10 points to be nice. So there's a 10-point curve in the grading. All right, let me not spend too much time on talking about that. Let us get back into the road to potential energy. Now, I'm going to try to get to explain what potential energy is today. We may or may not make it there, but here it goes, okay? So I need to take a little bit of a detour. And the detour is going to be on what's called partial differentiation. Partial differentiation. So how do you do partial differentiation? What is partial differentiation? It's very simple. I'm going to illustrate by example. I think we're on example, what, 6? 5? 5? Okay. Example 5 then. Partial x of x squared plus y squared, y cubed rather, and partial y of x squared plus y cubed. We'll start with this. The way the partial derivative works is simply this. You differentiate the variable and you hold the other one as if it's constant. So we don't think of y as a function of x. We think of x and y as being independent. That's what this notation announces to the world. When you write this funny, this is not a d. This is not me being sloppy. You've seen me write d. Is this my d? No. This is a partial, right? This is like a Greek d or something. But so partial x. This means, among other things, that x is being held independent from the other variable, which is y. So it's not implicit differentiation like we do in Calculus 1, where you'd have 2x plus 3y squared dy dx. Not at all. The key idea here is partial y, partial x is 0. And partial x, partial y, those are 0. That's a guiding principle here, if you want. So this is just 2x. And do you guys want to tell me the second one? 3y squared. You guys must be in Calculus 3 because you could answer that question, are you? No, you're not, right? Maybe you are. Somebody in here is in Calculus 3.